Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. So in the previous lecture, as we've seen that the study of these matrices is of paramount importance, because essentially over finite dimensional vector spaces, every linear map can be captured through matrices. More importantly, we then launched into a study of what are known as linear operators, that is linear maps from a vector space to itself. And these are captured in turn by square matrices. And one of the most important properties of these square matrices happens to be these eigenvalues and eigenvectors, which are a consequence of something that we've studied earlier, that is invariant subspaces, right? So we saw that corresponding to these eigenvalues, we can cook up some of these special invariant subspaces, which we denoted through this curly E's in the previous lecture. We then ended in the previous lecture on the note that if a matrix has all its eigenvalues distinct, right, complex but distinct, then such a matrix is always diagonalizable over the field of complex numbers. Right? What does that mean? That means that it's a diagonal matrix. Of course, the diagonal entries need not be real, they could be complex. If you allow for that, then such a matrix is always diagonalizable, and we also proved that by showing that for such a matrix you will always have a bunch of n linearly independent eigenvectors, which then naturally lead to this similarity transformation, which allows you to diagonalize such a linear operator captured through a square matrix. Now it turns out that this is a restrictive class of systems or class of operators which can be diagonalized, right? In general, however, if you want to come up with the exact class of operators that can be diagonalized, then we will have to understand something known as sum of subspaces. Remember, this is not a sum of vectors with which we are familiar, this is a sum of subspaces, and therefore we need to define what this is. It is not very difficult. So here goes. Suppose W1 and W2 are subspaces of V. So in other words, we are saying that W1 is a subspace of V, the vector space, and W2 is also a subspace of V, which is the original vector space, right? Then we define the sum of the two vector spaces W1 plus W2. So it is defined in the following manner. It is a collection of all vectors W belonging to the parent space V such that W can be expressed as the sum of two vectors W1 and W2 where W1 comes from the vector space big W1 and W2 comes from the vector space that is big W2, which are in turn subspaces of V. So this is a collection of all such vectors which can be expressed as the sum of two vectors, one of which comes from W1, the other comes from W2, right. At this point we are not saying that this is a unique representation of this small w. If it is, then instead of saying or calling this a sum of vector spaces, we would have called it a direct sum of vector spaces. Okay. So, I leave it to you to check as an exercise that this is indeed a vector space. Yeah. What do you have to check in order to do that? Recall that in order to verify that a particular object is indeed a subspace, that is W1 plus W2 is indeed a subspace, you have to pick out any two fellows in W1 plus W2 which satisfy this definition that I have just written down, take their linear combination. So, alpha 1 times the first vector plus alpha 2 times the second vector, where alpha 1 and alpha 2 are scalars, right. In our case, scalars will be, as I have said so many times, either real numbers or complex numbers. And then you have to check whether that resultant combination is also a member of this W1 plus W2 set that we have now defined. If it is, then we say that this W1 plus W2 is a subspace. So, I am already claiming it is a subspace. All I am asking you to do is to check that it is indeed a subspace. Take that as an exercise. Okay? All right. Now, once we have convinced ourselves that this is a subspace, we then go into this condition for a linear operator to be diagonalizable in its matrix representation. What is that condition? It turns out that, recall what we had defined in the earlier lecture as these subspaces E's, you remember? Let me just go back there, yeah. So, this is what we had defined as the subspace E, right. So, we revert to this particular definition that we had presented in the previous lecture, right. So, if you have lambda k as an eigenvalue of A, the matrix A, then you take the kernel of lambda ki, I is the identity matrix. So, lambda k times I minus A. So, of course, by dint of the fact that the kernel is itself a subspace, this E k will also be a subspace, right. So, it turns out that even if your eigenvalues are not distinct, okay. So, I am not going to prove this result, but you can see that it clearly follows from what I have just discussed. Of course, you need a different line of approach probably to prove it. Maybe you can use mathematical induction, but what I am saying is that if E1 plus E2 plus dot 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 till Ek, yeah, is equal to Cn, right. So, if indeed those kernels that we have defined, so where of course lambda 1, lambda 2, lambda 3, these need not be distinct, all right. Okay, so this is not k, I am sorry, this will be actually for n, all right. So, if they are not supposed to be distinct, then we can always take them in isolation. So, for example, if there are repeated eigenvalues, then you take them as many times as they appear according to their algebraic multiplicity, right. And if you can find n such subspaces, right. So, each of these will be naturally one dimensional. In other words, if an eigenvalue is repeated k times, or let us say 5 times for example, then you must also have 5 linearly independent eigenvectors corresponding to that particular eigenvalue which is repeated 5 times. Yeah, in that case maybe E1, E2, E3, E4, E5 are all corresponding to the same eigenvalue, yeah, but they all generate these different kernels. Yeah, so there are 5 distinct eigenvalues, it is a 5 dimensional. So, the kernel will be 5 dimensional. So, the way I have written it, these are all 1 dimensional, yeah, but if you combine them together, right, then it would be that you would be saying that, well, Ek has to be exactly of the same dimension as the algebraic multiplicity, or as many times as the particular root appears as a root of the characteristic equation. Yeah, after all, the root of the characteristic equation is what gives us the eigenvalue, right. Anyway, so this, so let me not just write this if and only if like this. So, this turns out to be an if and only if condition, okay, for A to be diagonalizable. Now, of course, you might think, okay, if the eigenvalues of A are all distinct, then we have already seen it is going to be diagonalizable. Even if they are not distinct, but if they manage to generate exactly as many linearly independent eigenvectors in the kernel as the number of times that eigenvalue is repeated as a root of the characteristic equation, even then it is diagonalizable, right. So then you might wonder, then well, it seems like almost everything is diagonalizable, so why are we even worried about this? So just to show you a quick example of a matrix that is indeed not diagonalizable, let me pick out this particular choice 0 1 0 0. Okay. Now you consider this matrix and you will immediately see that the eigenvalues are 0 and 0, right. So there is an eigenvalue at the origin which is repeated twice. So the algebraic multiplicity, I mean if you take the characteristic equation of this, that is going to be s squared. Yeah, this is the characteristic polynomial. So the characteristic equation will be s squared is equal to 0. This is the characteristic equation, right. And if this is the characteristic equation, then you know that the algebraic multiplicity of 0 as an eigenvalue is 2. Unfortunately, the moment you try to solve for lambda I minus a times v is equal to 0, well lambda is of course equal to 0 itself. In other words, you are trying to solve for a v is equal to 0, you will end up with a problem. As you can see, it is 0 1 0 0 and let v be written as v1 v2 like so. You will immediately notice that this leads us to conclude that v2 is equal to 0 and v1 could be any real number, right. So that means that any vector of the form, so the span of 1 0 is equal to the kernel of 0 times I minus a, yeah, and clearly this is of dimension equal to 1. So therefore this is also of dimension equal to 1, yeah. This has a name, this is called the geometric multiplicity of the eigenvalue. So in order for diagonalizability to hold, you must have that every eigenvalue must satisfy the condition that the algebraic multiplicity must be equal to its geometric multiplicity. In this case, this is violated. So it clearly violates this condition that I have just given here. Let me just box that out, right. So there are further analysis that lead to something called a Jordan form. We will really not discuss the how of the Jordan form, rather in the sequel, after we have clarified this point, we will move over to the position where we will say that, well, we understand that this Jordan form always exists, but we are interested in some properties of this Jordan form that will subsequently in later lectures aid us with some proofs or some results, right. So we will really not launch into a proof of the existence of the Jordan form and how to constructively get a Jordan form, what those Jordan chains are, what the sizes of the Jordan blocks will be, right. Those will be part of an advanced linear algebra course, right. We will not get there. We will assume that the listener or you will always have adequate material to refer to in order to find out the constructive way of obtaining the Jordan form, right. Many standard textbooks, if not all, on control theory at least have these ideas discussed, if not in the main text, then at least in the appendices, right. So please do go through them if you are interested. We will not really discuss the how question here, right. Anyway, the point being that we are in trouble here because we can't diagonalize this matrix, right. It turns out that this matrix is not just a flash in the pan. It is not an exception to the usual rule. There will be always invariably certain matrices which do not satisfy this condition that every one of its eigenvalues has the same algebraic multiplicity as the geometric multiplicity, right. And in such case, there is no hope for us to be able to diagonalize such matrices and therefore such linear operators. So then what do we do? It turns out that the next best thing we can do in such cases is to get to the Jordan canonical form using a similarity transformation. So, before we actually formally state that result without proof, of course, I would just like to highlight and discuss a few things, few aspects of this Jordan canonical form which might be of our interest. Okay. So, what does a typical Jordan form look like? I mean, what are we shooting for? We knew earlier that we wanted to get from this A to this T inverse AT, which is a diagonal matrix, and we know what this looks like. This looks like lambda 1, lambda 2 dot 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 till lambda n. Yeah, this is what we were trying to get at earlier. But now that such hopes have been dashed, we know that when at least one of the eigenvalues of a matrix does not have the same geometric multiplicity as its algebraic multiplicity, then there is no hope for getting this diagonal form. So, then we shoot for a Jordan form, which is nothing but a generalization of the diagonal form. It is a block diagonal form. Not just that. So, what we are shooting for is something like, you get a T inverse AT. Instead of having just the diagonal entries here, we will have some block diagonal J1, J2 dot 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 till JK, let us say. Okay. So, each of these are now block matrices, right, where everything else is 0, right. So, the next best thing to a diagonal matrix is a block diagonal matrix. Not just that, if we look closely, if we zoom in on each of these individual blocks here, any one of these individual blocks here, they also have a beautiful structure. Yeah, they have an upper triangular, not just an upper triangular again, but only upper triangular to the extent that they have a diagonal that is non-trivial potentially, and the first super diagonal, and that is it, right. So, each of these individual blocks that we have here, the Jordan block, let us say Ji, it looks something like this, lambda, lambda dot 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 till lambda, yeah. And then the super diagonal has 1, 1, 1, rest everything is 0. So, what are we trying to get at? When we cannot diagonalize, we get to this Jordan form, Jordan canonical form. What is the Jordan canonical form? Jordan canonical form is a special form where if it is not diagonal, at least it is block diagonal. Then we get a little more tempted towards asking the question as to whether individually these blocks can also be made to look beautiful, right. So, we grow emboldened to ask that question, right. And then we find that this Jordan canonical form, not just that it gives us this block diagonal form, but these individual blocks themselves, that is, if you peer closely into these, they also have a beautiful structure. They are upper triangular. And look, we go one step at a time. Upper triangular is already a good form to have, yeah. Remember, when you tried to solve a system of linear equations, if you had upper triangular, then you solve the last equation first and you use back substitution to solve back subsequent equations, right. Similarly, if you have a dynamical system given by x dot is equal to ax plus bu, and if A matrix happens to be upper triangular, then the last equation is at least completely decoupled from the rest, right. So, the last equation you solve for xn, you have xn dot is equal to something times xn, solve for xn independent of the others. Then you, once you have the closed form expression for xn, plug that in the expression for xn minus 1. So, then you solve for xn minus 1 dot is equal to something times xn minus 1, that something is basically what is sitting in the diagonal of that matrix, plus something else times xn, and now that something else is going to be the entry in the nth column and the n minus 1th row, and the xn can already be obtained in the closed form from the preceding step, right. So, it is exactly like back substitution. So, already we know this upper triangular form is beautiful, and then we grow emboldened to ask, can we make this upper triangular form also further even more beautiful, because ultimately we want to narrow it down. The diagonal form would be the best, every single equation is decoupled, but upper triangular is not a bad deal either. But what is even better is, even among the upper triangular matrices, this individual Jordan block, if you look closely, it does not necessarily contain all non-zero elements in the upper triangle, right. Only the first super diagonal has non-zero entries, that too each of them being unity. Yeah. So, this is an excellent form to have, just short of the diagonal representation or the diagonalizability. Yeah. And what is even more startling and amazing is that even if you cannot diagonalize a matrix, there will always exist a similarity transformation that allows you to get to the Jordan canonical form. Yeah, it holds for every square matrix and therefore for every linear operator, right, and or its matrix representation, that is, right, and that is very good news for us, right. For us means those who are interested in studying these linear maps, these dynamical systems represented in the state space form given by x dot is equal to ax plus bu, right. Okay. So, why that is one way of showing this, but now we will try to use a little more sophisticated language to potentially explain the same thing, but recall that in the previous lecture we have already introduced to you the notion of invariant subspaces, right. So, let us focus for the moment on this individual Jordan block. By the way, before I forget, remember that when you are representing this in the Jordan canonical form, you might be tempted to think that this J1, J2, so on, these are all Jordan blocks corresponding to distinct eigenvalues, but that is, I want to really emphasize this, that is not true at all. You could have the same eigenvalue throwing up multiple Jordan blocks in the overall Jordan canonical representation of different sizes. What the sizes would be, how many such blocks would be there, again we will not get into finding the answers to those questions, because that will take us too far afield into advanced topics on linear algebra. But there are, I assure you, constructive ways of obtaining these Jordan canonical forms. Okay. So, that is one subtle point which I think warranted clarification. So, now that we are past it, let us go back to this, looking at this individual Jordan block and trying to find out what other beautiful or attractive features does this have. Okay. So, look at this Jordan block form here now, right. This Ji can now be written as lambda I. Suppose this is a K cross K matrix, or rather maybe not K, let us call this L cross L matrix, right. So, this is basically an identity of size L cross L plus a matrix N. What is the N matrix? This N matrix basically captures the super diagonal. All right. Okay, let me write the, yeah. Yeah. So, this is what this matrix N looks like, right. Remember, it has zeros everywhere except on the first super diagonal. Super diagonal means the one just above the diagonal, right, and the entries on the super diagonal are all unity. What is the feature of this N? Check that N squared, I mean again you can take this as an exercise, it is not really that difficult to see. When you look for N squared, you will see that these are all shifted one position to the right. What I mean by that is that in N squared, you will see that the first row of N squared becomes the second row of N. That is not really surprising to those of you who are paying attention to what is going on here. Yeah, what does a pre-multiplication to a matrix do? What does a post-multiplication of a matrix do? If you just try to visualize that, you will immediately see that this is what happens. So, now in N squared, the second super diagonal has this ones. So, how many ones were here? This one had N minus, or sorry L minus 1 non-zero terms. Now, this one has L minus 2 non-zero terms. Yeah. So, proceeding along the same line of reasoning, yeah, can I not say that n to the power L is going to be basically an all zeros matrix, and such matrices which when raised to a certain power lead to the zero matrix, they have a name, they are called nilpotent matrices. So, therefore, n is a nilpotent, so this is nilpotent of order L in this case, right. So, when we have this sort of a representation, you see each individual Jordan block, yeah, can be represented as a sum of a diagonal matrix where each of its diagonals are identical, and a nilpotent matrix which when raised to powers of L or above go to 0, right. So, that is essentially the a chief attractive feature of this sort of a Jordan canonical representation, right. Okay. Remember that if you had a general upper triangular matrix, you keep multiplying it, you will keep getting upper triangular matrix, yeah, but you cannot have hopes of having a nilpotence, right. But because this is a very special upper triangular matrix where only the first super diagonal is non-zero, it leads to nilpotence, right. So, that is one appealing feature of this Jordan canonical form. But is that all? Let's try to investigate what sort of invariant subspaces, yeah. So, the question is, what kind of J invariant subspaces or Ji invariant subspaces can we see from Ji? Yeah. So, look at the structure of this Ji. This is the structure of the Ji, right. And now try this. Consider, what should I call it? Let us say P1 is equal to span not spam, span 1 0 0 0, okay. All right. Consider P2 to be span 1 0 0 0 0, comma 0 1 0 0 0 likewise, yeah. So on till what is the size of this? This is of size L. So, let PL be the entire CL, right, because you see where this is going, right. The first one I picked the first standard basis 1 0 0 0 0, yeah. The second one I pick the first two standard bases, and finally when I pick all the n standard bases over the field of complex numbers, this basically spans the entire CL, right. So, these now I put to you that this P1, P2 till PL are all invariant subspaces, or rather Ji invariant subspaces. Is there a way to check? You bet there is. You just take any vector that belongs to P1, which is basically C times just 1 0 0 0, and you operate using this Ji on it. What do you get? What you get is basically this matrix pre-multiplying a vector of the form C 0 0 0 0, so on and so forth. What would be the result? You see, when you operate, when you multiply this first row with such a column, only the first entry reflects. When you start multiplying through the second row onwards, because this second row's first entry is 0, you will keep getting zeros, right. So, therefore, I ask you to check that Ji times Pi, yeah, belongs to Pi whenever Pi belongs to Pi. Yeah, that is basically the definition of invariance, right? Just check. It's not very hard to see. You just have to look at the structure of this fellow, right? So basically this J reveals to you all that this Ji reveals to you all its invariant subspaces in a very transparent manner. You see that from a block of size L cross L, you have all these L invariant subspaces, right? So that is, very straightforward and very apparent. Now we are going to go up one level. From just looking at this Ji, let us look at the original matrix J, which is the Jordan canonical form, right? So let us look at J now, and say we have J1, J2, don't know what index I use there, maybe K, right? Yeah, JK. So we have JK, right? And let S1 is equal to, say, and okay, let's also define this J. How did we get this J? We got this J by T inverse AT is equal to J. In other words, we can always write that AT is equal to TJ, right? Keep this in mind. This is going to be very handy now in whatever we are going to now discuss, right? So let S1 be the image of T1, yeah, where T1 is the submatrix containing the first L1 columns of T. What is L1? So we say that Ji belongs to C Li cross Li. So each Jordan block, the k Jordan blocks that we have here, each Jordan block is of size, the ith Jordan block is of size Li, right. So I am saying that I am taking the first L1 columns of this matrix T, right. Then from this relation that we have here, if instead of considering this entire T matrix, we just consider the first T columns of A, Ti columns of A, right, T1 columns of T. So this is basically like I am saying I am partitioning this and T bar, and this overall whole thing is T. This is the same as writing T1 and T bar. So of course this is of size L1 and this is of size n minus L1, that many columns are remaining, right, times J. Now you notice something very interesting here from this particular relation. If I just focus on this first, on the left hand side I have the product of two matrices, on the right hand side I have the product of two matrices. Left hand side the matrices being A and T, right hand side the matrices being T and J, right. If I focus on the, so entry by entry they are equal, so column by column also they are equal. So let me focus on the first L1 columns on the left. So the first L1 columns on the left give me A T1, right. What about the first L1 columns on the right? And this is something fascinating. If you think for a moment, if you think about it for a moment, you see the structure of this J here plays a huge role in this. Notice that because these are all 0 blocks here, yeah, so on, of course, notice that because these are all 0 blocks here, what do I get when I pre-multiply this J by a T? You see this is going to pluck out the first L1 columns of this matrix on the right hand side is going to pluck out what? Is going to pluck out T1 times J1. What does that mean? Why am I saying this? Because recall, now with this block matrix you can treat this like the usual matrix, and if you try to look at the multiplication here, right. So you sort of, okay, let me rewrite it here to make it more transparent. Yeah, all right. So suppose you have this T1, T2 dot 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 till T, what was it, K, I hope, right. So this is of size L1, this is of size L2, so on and so forth, this is of size Lk, right. We can always write it like this. Of course, I was earlier considering this entire thing to be like T bar. So this is of size n minus Lk, n minus L1, I am sorry, right. And now if we consider this J1, J2 likewise till Jk, so these sizes are all compatible. Yeah. So this is 0, right. Yeah, fantastic. So now if I want to find out the first L1 columns of this fellow, what do I get? I just see that this T1 multiplies with this J1, this T2 multiplies with this 0, so on and so forth, till every one of them gets multiplied by 0, a block of zeros. So therefore what I then have is just nothing but T1 J1, right, plus some zeros, 0 matrices. So that eventually leads to just T1 J1 because of this structure, you see, because of this block diagonal structure, and therefore this relation you can immediately see is valid, right. But what more is revealed from this relation? It tells me that, well, if I take this S1, where have I defined it? Yeah, this S1, remember, which is nothing but the image of the first L1 columns of the matrix T, that matrix T which through a similarity transformation leads me to the Jordan canonical form, right. So if I take this subspace, of course this is a subspace because it is an image, we have already established that an image of a matrix is a subspace, right. In fact, image of a linear operator or a linear map is also a subspace, we have seen much more than that, right. Okay, good. So now if we have seen this S1, so what can I say about S1? You see, if you allow this linear operator A to act on any vector in S1, what do you get back? You get back nothing but, now think of this J1, what does this J1 look like? This J1 looks like lambda, lambda, so on, lambda, 1, 1, 1, right. And then you have this T1. So this T1 will contain maybe columns like T1, T2, so on till TL1, right. So what is this going to tell me? This is what this fellow looks like, doesn't it? So this is going to be nothing but, when I operate this and the first here, this is going to be lambda times T1, right. That is basically it, all right. What I get in the second time I operate this is going to be T1 plus lambda times T2. Yeah, finally what I would get is TL1 minus 1 plus lambda times TL1. That is what I am going to get, is it not? And on the right hand side, what did I have? I had A times T1, T2 dot 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 till TL1. So what I then get is, very interestingly, you see, A T1 is equal to lambda T1, A T2 is equal to T1 plus lambda T2, so on till I get ATL1 is equal to TL minus 1 plus lambda times TL1, right. What does this tell me? Look, this set of vectors T1 through TL1, these are linearly independent and they span a subspace that is S1. Why are these linear independent? Because they come from a matrix T which is invertible. So, if a square matrix is invertible, then all its columns are linearly independent and therefore a subset of its columns is also linearly independent. This is a very fundamental result. Subset of a linearly independent set has to be linearly independent. If not, then what happens? Then you build on any and you append any other vector, it can no longer be linearly independent. So, subset of a linearly independent set is linearly independent. T matrix is invertible, therefore all its columns are linearly independent and therefore any subset of the columns of T is also linearly independent and therefore its span already has this basis which is nothing but these vectors themselves. So, this T1 through TL1, the first L1 columns of T, they form a basis for this subspace S1, right. And once I figured out that no matter which element you pick from this basis, once A acts on this element, it sends it to a fellow in the same subspace. Look, this belongs to S1, this also belongs to S1, each one of these belong to S1. What does that tell me? That tells me that S1 is A invariant. And this is a great result because now what I have here is that through this Jordan canonical form, right, through this Jordan canonical form, I have found these subspaces that are A invariant. Yeah. In fact, I can now take the first two Jordan blocks, right. I can take the first two Jordan blocks and I can say that, well, let me take any vector that belongs to this particular subspace, right. So, let me take for example S2 could be the first, so span of maybe how did I depict it, T1, T2. So, it could be the span of this, or rather image of, sorry, it is now an operator, no. So, we can write it as an image. So, this is an image of T1, T2, right, where of course, this T1 is L1 columns and this is the next L2 columns. Yeah. So, if you define your S2 to be this, then also you will see that the S2 is also A invariant. Yeah. So, we have the rudimentary blocks S1, S2, S3 like this, you can keep appending. In fact, they do not need to be consecutive either, right. You can take the first L1 columns and then you can take maybe L3 columns, you can leave the next L2 columns and you can take L3 columns. Yeah. And you take any vector that belongs to the image of T1 and T3, yeah, and you will see that eventually, of course, subject to this choice of basis, yeah, you can take this, you have to keep the zeros in between then, right. You have to remember that you are omitting this T2, so you are taking the image of T1 and T3, right, and you take any vector that belongs to this, the image of T1 and T3, and you will see that that is also A invariant, right. So, you can keep taking these, this gives you a very nice building block for invariant subspaces. That is what the Jordan form does, does not it, right. So, you already see this construction, that is why this Jordan block in our sophisticated language of invariant subspaces is so beautiful, right. But if once again, so we are doing a bit of back and forth, once again we want to go deep into this individual S1 now. Already we have studied this Ji at some depth, right. So, we have seen that this Ji itself throws up Li, J invariant subspaces, right. And if you pry closely inside those blocks inside Ji, you will see that hidden within them for every one of those J invariant, Ji invariant subspaces, yeah, you will be able to find some A invariant subspace. Remember we said that there are basically Li J invariant subspaces, Ji invariant subspaces, this is P1, P2 through till PL, right. We have already given you construction of these, right. We have already given you these Ji invariant subspaces. If you can append them suitably with zeros, yeah, you will see that you can get corresponding to these subspaces, you can also get A invariant subspaces. Okay. Take that up as an exercise to convince yourself that these J invariant or Gi invariant subspaces in turn themselves lend themselves easily to the construction of A invariant subspaces in turn. Okay. So, that is the one bit of takeaway message that should be transmitted from all of this study or analysis that we have done so far. Yeah. The idea of these invariant subspaces is very, very powerful, okay, and will come in very handy throughout our analysis, alright. Okay. So, now we will put an end to this discussion on invariant subspaces and we will start to look at something else. Since we are already dealing with matrices and we will encounter matrices throughout this course and we will harness many of their properties, the next ideas that I am going to try and sort of introduce are those of self-adjoint matrices or operators. In the complex domain, these will then lead us to unitary operators and the idea of what is known as positive definiteness. Okay. The idea of this positive definiteness is very important because we have to understand what this positive definiteness means in order to appreciate or grasp the ideas of LMIs, linear matrix inequalities, that we shall be using throughout this course, left, right and center, right. This whole course of robust control will be built, at least a huge chunk of it will be built on an understanding of LMIs, right. So, therefore, we need to understand this notion of self-adjoincy, unitary matrices and positive definiteness. So, you know, self-adjoint matrices, these are, I mean, it might seem like a term that is not very familiar, but I assure you that if you have done a course on matrices, you already have encountered these objects. So, we say that this n cross n matrices, n cross n complex matrices Q such that Q star is equal to Q. When I write star here, what I mean is that I am not just taking the conjugate of each individual entry, but I am taking a transpose. So, just to illustrate through an example, if I say that my matrix A is 1 plus 2j, 2 plus 3j, 3 plus 4j, 4 plus 5j, right, then my A star will not just have individual entries conjugated as complex numbers, but also we will have to take the transpose. So, of course, the diagonal entry does not change position, only gets conjugated. The off diagonal entries, because it is a 2 by 2 case, it gets flipped. So, that row becomes the column becomes the row, right. Right. So, this, so if A is this, then yeah, the adjoint of A, yeah, is going to be this, all right. So, such a matrix where it is equal to its adjoint is known as a self-adjoint matrix or a self-adjoint operator. Okay. Clearly, in this example, the A matrix is not a self-adjoint operator because these two are not one and the same, right. Okay, good. So, having understood this, we will now sort of, okay, the other important result here is that, of course, you are familiar with this and a moment's thought will reveal itself to you that this is pretty obvious, is that if you have two matrices, say A and B, such that you take their conjugate transpose as it were, then that is equal to nothing but the individual conjugate transpose of B multiplied by the individual conjugate transpose of A. Yeah, the order gets reversed, just like the transpose operation, right? It's exactly the same. So this is an important property that we do well to remember throughout this course. Okay, so now having seen this, immediately what will follow is the idea of this length or norm of a vector. Again, you are familiar with this, but since we are dealing with complex numbers here and complex n tuples here, so for x in Cn, we say that, of course sometimes people use a double line, double vertical line, but we can also use a single vertical line like we do for the modulus of a complex number, whichever notation you feel comfortable with, but stick to one notation, right. This is going to be either, so this either you use this or you use this, okay, or whatever floats your boat. So this is just nothing but, you see, if it is a vector, then when you take its transpose conjugate, it becomes a row vector and each entry becomes conjugated. So this, and you take its under root. And why is this under root bound to exist? Because of course this is nothing but, you know, the summation of the moduli of the individual entries in the n tuple. Yeah, that is what this is. So it is bound to be positive, right. It can only be 0 when the vector itself, when x is equal to 0. Yeah, so this is something that we call as the norm, okay. So this is the norm, right. Not a very difficult object to remember, but one that will be of immense significance, right. So let us formally define this Hn. Sometimes this is called self-adjoint, or also called the Hermitian operation, okay. Once we have this sort of a Hermitian operation, we are also interested in seeking out what sort of eigenvalues will a member of Hn have, that is any one of these Hermitian matrices, what sort of eigenvalues can they have. So suppose Q belongs to Hn, which basically means that Q is equal to Q star. So let us take any one of its eigenvalues. So we have Q times x is equal to lambda x. Well, lambda is obviously an eigenvalue. I am not writing this in detail, yeah, it is not after all linear algebra or a matrix theory course, you understand what it means. So this is an eigenvalue which can be a complex number, and this is an eigenvector which obviously belongs to the complex n tuples, the space of complex n tuples, right. Okay. Now suppose I hit it on the left with an x star, yeah. We have already seen what those x star objects are. It is a vector. If x is in Cn, x star is in C1 cross n, right. So we have this, and then we have lambda times x star x. But what about this x star x? What do I know about this? We have just defined this, right. This happens to be the norm, right. So we can just write this as we have just defined, this x star qx is equal to lambda times this x whole squared, which is a positive number, of course. It is a square of a I am sorry, it is a square of the norm, so it is a positive number, right. But now on the other hand, so let me just put that inside a box because it is a special relation. On the other hand, from the preceding line of attack, yeah, from this line of approach, if we had taken another route, we can also say that x conjugate q conjugate x is equal to lambda x conjugate x, right, or x, you know, this is the norm squared of x, right. Why can I write this? Because remember we started with the property that q is equal to q star. So, we have just replaced this q. So, we are just replacing this q with this q star, alright. Once we have done that, now remember this property, this A B whole conjugate, whole Hermitian transpose conjugate is equal to B transpose conjugate times A transpose conjugate. So, I am just using that result here, and I can say that this is Qx whole conjugate times x, and on the right hand side I have lambda times x squared. So, from these two boxed relations, what can I deduce? Can I not just replace this part now? Let me go back to the blue color. Can I not just replace this with lambda x whole conjugate? So, that is basically inherited from here, times x is equal to lambda times mod x squared, right. But what does that tell me? That tells me that this lambda is a scalar, right. So, this I can pull out, of course, after conjugating it. So, this is lambda star, right, this is lambda star, and what I am then left with is this x star times x is equal to lambda times this x squared. Yeah. So, see, we have first used this result that this is going to be equal to this from this box bracket, and then we have used the fact that this q is equal to q conjugate transpose because it belongs to Hn, so Hermitian, right, and therefore, we then replace this with lambda here. Already we have inherited this property here, right, from this it directly followed here, right. And now, we say that this lambda starred times this is equal to lambda times the same quantity, and this x, remember, is not a 0 vector, because of course an eigenvector is a non-zero, non-trivial vector by definition. If it is a 0 vector, then anything can be an eigenvector, right. 0 vector is always like going to be an eigenvector for 0 eigenvalue, but that is not the case, that is not the way it is defined. In the definition of eigenvector itself, we always consider that it is going to be a non-zero vector, the non-trivial null space of A minus lambda I, that is what qualifies as an eigenvector. So, therefore, we can cancel this out from both sides, because this is after all a scalar. What we then have is that the lambda star is going to be equal to lambda. So, that means the significant takeaway from all of this is that if you have a Hermitian operator represented by a Hermitian matrix, self-adjoint operator represented by a Hermitian matrix, then all its eigenvalues are going to be real, because remember, the only numbers which when conjugated lead to the same number have to be purely real, they cannot have an imaginary part. If they had an imaginary part, then it will never equal its own conjugate, right. So, the eigenvalues of such matrices are always going to be real, and that is an important conclusion, alright. So, the next idea we are just going to introduce and then leave it at that, and in subsequent lectures we are going to follow through with this idea of so called orthogonality, right. So, already now that we have defined this norm here, we will also define this inner product. We are not going to define the general inner product, because inner products can have different forms, lots of different forms depending on the vector space in which you are talking about. The same vector space can have multiple different inner products, in which case they might be the same vector space, but in the sense of inner product spaces they become different spaces. We are not going to get into those fancy kinds of inner products as of now. We will only talk about the conventional inner product which you are already familiar with by virtue of your knowledge of dot products, right. So, we will say that if x and y belonging to this n tuple of C is such that you have x star y, that is the complex conjugate transpose of x, which is basically a row vector, times y, which is a column vector, is equal to 0, then x and y are orthogonal to each other, right. So, if we have a bunch of orthogonal vectors and further suppose v1, v2 dot 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 till vk is a set of orthogonal vectors. What I mean by that is, you take the inner product or this dot product of any two fellows in this set and it is always going to be 0. That is, vi star vj is equal to 0 for all I not equal to j. Yeah. Then if we further have the norm of vi is equal to unity. So, let us call this a set S, yeah. S will then, so let us rephrase this as and, yeah, S will then be called an orthonormal set of vectors, yeah. So, they are not just orthogonal, but because their individual norms are unity, they are going to be called an orthonormal set of vectors, okay. So, we understood what orthogonality is in terms of this inner product, this dot product like inner product we have defined, okay. And now we understand that if we have a set of vectors which are all mutually orthogonal, so you take any two fellows among them and take their inner product and they happen to be 0, right, then it is called an orthogonal set. Over and above that, if each of these individual vectors happens to have a unity norm, then they are not just orthogonal, but they are orthonormal. In the next class when we come back, we shall start with this derivation or start seeing this condition that an orthonormal set is always going to be linearly independent. You can already give it a try before we meet next, yeah, before you watch the next lecture. That will be the first thing we will do in the next lecture. Till then, take care. Thank you.